Good morning, Alok, Ori.
Um,
Yeah, what happened today?
Nothing, ma'am.
Why so low strength?
We had a class previously, so that's why we late.
The students are yet to join?
Yes, ma'am. There were 100 students in the last class. They might come.
Okay, okay. I'm sure there are no quizzes yet.
No, ma'am.
Okay. So anyone having any doubt from the previous classes? Else, let's start out. And today I'd like you to work on paper pencil. Take your copy with along with you or a paper sheet with you. And we'll take up a very small problem and we'll try to design the circuit. Though it is a very simple one, but still let's go through the process. Okay, so we will do a problem. We are doing, remember, synchronous circuit, sequential circuit design. But what we are looking at is a serial adder. So if you see the block diagram, this is, let's say, operand A, and it could have any number of bits, 4, 5, 8, or whatever. Doesn't make any difference to us. Similarly, this is register B or operand B, which has stored information about the operands. The operand size can be anything. It could be 4-bit, 8-bit, 16-bit, 64-bit, or any number of bit. The circuit should work. So we are designing this serial adder. So what it'll do is it'll take one input A, another input B, one bit at a time, starting from LSB. Okay, so least significant bit will come first. Okay, and it will give the sum bit by bit. Okay, so you will generate, if there are n bit numbers, you are generating a n bit sum out of it. Okay, so you need to design the circuit for this serial adder. This we know, these are registers. So if I'm using n bit operands, I need n bit registers to store the information. Okay, though n does not make any difference, but you can take it as 8-bit to start with. Yeah, Aditya Kumar. Have you got the problem? 5139. Vedang, Vedang Mishra. 5147. I don't like it. If don't connect if you are not interested in attending the class. Abhishek 5041. Abhishek, are you there?
Ma'am,
Yeah.
ma'am, Akashi, ma'am, you called me.
I didn't call you yet, but
Okay.
yes, if you are listening, Okay. Did you understand the problem?
Ma'am, actually, I missed the last few classes, so I'm unable to get it right
So
now.
you should go through them. Na? We have a class alternate day. We never have consecutive class. So I think 1 or 2 days are good enough to go through the previous class if you have missed it.
Yes, ma'am, I'll go through them.
So I won't be able to explain everything again and again when recordings are available.
Yes, ma'am, I'll
Yeah.
go through them.
Aditya Kumar, are you now available? Aditya Kumar, either mute yourself or respond. 5139. Okay, let me find out someone else. Dhruv Agarwal. Dhruv Agarwal, are you there? I am marking all the absents. जो respond नहीं कर रहे हैं वो सबको मैं आज attendance बिल्कुल नहीं देने वाली हूँ. Daksh Marwa. Okay, so क्लास में कोई भी प्रेजेंट नहीं है. जो प्रेजेंट है वो हैंड रेस कर लो. और अगर कोई भी नहीं है क्लास में प्रेजेंट, या गुड, there are at least few people who are listening to me. Yeah, nice to see you. Digambar Dhamija, have you understood the problem?
Yes, ma'am.
Okay, so let's write the FSM. Okay, Ishika,
Yes, ma'am.
have you understood the problem?
Actually, I joined a bit late. I was
My screen is still visible. I'm asking you to design a FSM for serial adder, which is taking 2-bit input at a time. So there are two operands A and B. Let's assume they are 8-bit, though bit length does not matter in this finite state machine. Okay. And you are reading these two input bits and you are generating sum bit by bit. Kashish Goel.
Yes, ma'am.
So are you able to write this finite state machine?
Ma'am, I have not attended the last lecture, so I'm not able to answer the question.
So put your hand down.
Okay, ma'am.
Tanya Sood. सबने हैंड डाउन कर लिया कि कहीं हमसे ना पूछ लें अब, है ना? Okay, I still have one person still raising hand, so let me talk to. इसने भी फटाक से. I don't know what's wrong with you. Why don't you want to do anything? Please understand, these are the subjects. If you do not practice, you won't be able to do. Dhruval, are you there?
Yes, ma'am.
Have you understood the problem?
में एक बिट आ रहा है और उसका सम करना है.
हाँ, तो let's write the FSM. Draw the FSM for it. Venn diagram first. सब कुछ मैं करके दे रही हूँ, बच्चे लोग रिस्पॉन्ड नहीं कर रहे हैं.
मैम इसकी स्टार्टिंग में 2 होंगे ना, जैसे पहले हम 1 स्टार्ट करते थे.
देखो ये है स्टेट मशीन, ब्लॉक डायग्राम. देखो रटे रटाए करने से कुछ नहीं होगा. अगर हम ये नहीं बना पाएंगे स्टेट मशीन्स तो पढ़ा लिखा सब बेकार है, हार्डवेयर में जॉब नहीं मिलती अगर आप नहीं करेंगे। मैं ये इन जनरल सारी क्लास को ही बताना चाहती हूँ। ये स्टेट है, ओके, एंड दिस इज योर सीरियल एडर। What is the state which is feedback? This is basically the information of partial carry. What else is required? This is the only thing required. So state machine is so simple that when you start on the bit 1, you are on state this, let's say P. Okay, what is the state? My input carry is 0. I can get multiple options from here. I can have input as 0, 0, 0, 1, 1, 0, or 1, 1. These are the 4 possible combinations. Okay. You generate carry only when the combination is 1, 1. For all other combinations, your carry is 0. The sum will be different. So if let's say I get 1, 1, my sum is 0, but I have generated the carry. So my state is different than the previous one. Here my carry, partial carry was 0. Okay, here let's say the state Q, this will have my partial carry as 1. Now all other combinations will give me a carry out equal to 0, which is partial carry, which we are generating from every bit. So on this transition, if I have input 0, 0, both A and B are 0, 0, my sum is also 0. If I have inputs 0, 1, my output is 1. If I have input 1, 0, my output is still 1. But I remain in the same state that my partial carry is 0. Okay. Now, this is the only input combination which generates a partial carry 1. Okay. So I go to a new state. Now, from this state, if I know my carry in is 1, now I still have 3 combinations of input. I can get 0, 0, 0, 1, 1, 0, so on. Okay. Now see what will happen. There would be some cases when your partial carry will be 1, and there will be some cases when partial carry will become 0. So when does partial carry become 0? If I get input 0, 0, I had partial carry 1. So my sum becomes 1, but my partial carry becomes 0. So I come to state P. I return to state P. If I have input 0, 1, carry in is 1. So my sum is 0, but I remain in a state where I have a partial carry 1. If my input combination is 1, 0, again, since my partial carry was 1, my output will become 0, but I will be in the same state because my partial carry is still 1. If I have input 1, 1, again, partial carry 1 added to it gives me a sum 1, and the carry remains 1. Okay. So this is a very small state machine with just 2 states. ये आदित्य कुमार, तुम्हारी पीछे से इतनी डिस्टरबेंस है ना, तुम रिस्पॉन्ड कर रहे हो। So now you will unmute yourself when you want to talk to me. Aditya was creating a lot of problem. Okay, so this becomes the state machine. Does everyone understand it? If there is any doubt, anyone who has not understood it, please let me know. This is the first time we have taken 2 inputs. Output is still 1, and it is a very small state and a meaningful example. because this reduces lot of hardware. We will see in a minute how do you design it. We will draw the state diagram for it and state table for it. State diagram I have already drawn, and we will like to uh, come out with the final circuit. Is that clear to everyone? Now, since I have drawn a Mealy machine, you can see that my output is a function of the transition. That means function is dependent on input as well as on state. So it is a Mealy machine. Now, to write the diagram, state diagram for it, it's very easy. One way, what you do is we will assign the code later, but the first thing I am doing is I am writing today a table in a slightly different manner. I am writing the present state. I have only two present states, P and Q, and I am writing here combined next state and output, which is sum. Okay, and I'm dividing it. Now this, my input combinations are 4 0 0 0 1 1 0 1 1. Now for 0 0, if I'm in state P, 0 0 gives me the state P and output is 0. Okay, if I'm in state P with 0 1, again I'm in the same state with output 1. Same state, output 1. 1 1 state Q with output 0. If I am in Q state and I have input 0 0, I go to P state and my output is 1. For all others, I remain in the same state with output 0 in these two cases, and in this same state with output as 1. Okay, this is another way of describing the state table in alphanumeric form. That means using the state names. We have not assigned the code yet. Okay. Now, if I have to write the state table in a binary form, I need to assign the codes to my state. Since I have only two states, I need 1-bit code to be assigned to my states. So let's say I assign a code 0 over here and 1 over here. I can do either way. I can assign 1 here, 0 here. It makes no difference. The only thing is design will change. Let's say now I expand my table, the present state 0, 1, and now I divide this also into 2. Next state for 0 0 0 1 1 0 1 1. Similarly, this is my output sum for the 4 combinations. So I can translate directly from here. On these 3, state is P. So this is 0, 0, 0. This is 1. And unfortunately, I have not left any space. कोई बात नहीं, मैं इसको बना लूंगी. Okay. In 1, this is the next state. And if you draw the outputs, see these 3 outputs 0, 1, 1, 0, 1, 1, 0. Here it is 1, 0, 0, 1. So this is the binary state table which we can generate easily. Now you can also identify, since my state is a 1-bit state, I need only one flip-flop to design the circuit. Okay. Now one bit flip-flop, one flip-flop, one bit, that is what we are designing. So I need to choose which flip-flop we should pick up. Let's say I can even pick up D flip-flop. So let me first convert this to a table where I can draw the excitation table easily. So that means I should have present state. I should have my inputs. So I am writing IN for the two inputs A and B. So I have 1 bit present state, 2 bit input, and I can make the combinations. For present state 0, I can have input 0, 0. I can have 0, 1, 1, 0, 1, 1. Similarly, for present state 1, I have 4 input combinations. So I will draw all the combinations and make my table complete. Now for this, I can translate what do I want on next state, because my flip-flop values are dependent on what is my next state. Okay, and then I will write the next state values from here. So 0, 0, 0, 0, 1. So this becomes 0, 0, 0, 1. For 1, 1, it is 1. And then for 0, 0, it is 0. So 0, 1, 1, and 1. Now let's say if I have chosen a D flip-flop. I had been using T all the time. Let me use D flip-flop. So if I have D flip-flop, so what will be my D input? How I am going to excite the D input. So the excitation table for D input is whatever you want, put it there. So we put this same values. Okay. And then the last thing to put in the table is your Z, which is not Z, S. In our case, this is S. So S is the sum output. So sum also I can write from here. This is 0, 1, 1, 0, 1, 0, 0, 1. So this is my complete table. Now what I have to do is I have to draw the circuit. So if you recall, if I'm using a D flip-flop, this is the first thing which you need. Maybe I'm using a positive edge triggered flip-flop. Okay. The second thing is I need to know the combination, a combinatorial circuit which will generate my D from my present state and input. So I need to design the function. So I need to make a K-map for D and I need to make a K-map for S. So these are the two combinatorial circuits required. So if for D I do, maybe I can do it here. So this is my present state 0 and 1. And over here, I can write my input combination 0, 0, 0, 1, 1, 1, 1, 0. It has to be in gray. So I'll change the position. So for 0, and this I am writing for generating D. Okay. So for generating D, fill in the entries from here. So what does it say? 0, 0, 0, and this is 1. then I have 0 and all other 3s are 1. Okay, so I can generate, I can minimize this using 3 pairs. So what do I get is my D is equal to, yeah, D is equal to, this is present state dot, and this input is, let's say, A followed by B. So this is P present state into B. This one is plus present state dot A, plus this is A dot B. Okay, and you will see this D is coming out to be something what we used to have expression for carry. Okay, so D is this expression. Similarly, you can find out the sum expression. I think I will have to use the next page, no other option. I'm using this side of a space. So this is again my present state. This is A, B, which is input. Now see, this is 1, 2, 4, and 7. So 1, 2, 4, and 7. Okay, so what is the expression? Though I know if I try to write an SOP expression, it will have 4 min terms. There is no minimization possible. But on the other hand, I know this, if I reduce those 4 min terms, it will come out to be PS XOR A XOR B. Okay, and I had D, which was PS dot A plus PS dot B plus A dot B. Okay, so now I can draw my circuit. Now to this, you want to generate and provide a D input. So you can do it in various ways. One way is a 2-level circuit straight way using 3 AND gates and 1 3 input OR gate. Or you can take out something common and reduce a gate and increase the level. I am not doing any reduction of any kind, and I am using straight way classical. This is PS, this is A, and this is B, OR of the 3, and you get D. And to generate, and what is this PS? Basically A Q output from the flip-flop. So you can connect that too. Okay, and to generate the output Z, you can use 2 XOR gates. A and B, and again XORed with the same Q, and this is your sum bit. Okay. So every clock cycle you will generate one sum bit. Is that clear to everyone? Any doubt in this? If you have any doubt, please let me know. Now I am leaving you with a problem. Try and do the same using a Moore machine. Try it out. We want to do a serial addition, but we want to make a serial adder using a Moore machine. Rather than a Mealy machine, we have a Moore machine, which means that now output is not the function of input, and output will be function of the state. Okay, and you need to identify how many states do you need and how will you draw. Think about it and draw it. As soon as you have done it, raise your hand. I'll be watching it out, and I'll give you an access to share your sheet. Let me see who can do it. Anyone who does it, kindly raise your hand. Okay, and we will talk. You can send me, if you find it difficult to share on screen, you can send me WhatsApp and I will draw on the board. Yes. Any guesses? How will you do it? Anyone who has started doing it? Anyone who could identify the how many states do you need? Aniket Biswas. Akshat Gautam. The attitude is not good. Anushka Agarwal. Divanshu. आज तो मैं किसी को अटेंडेंस देने नहीं वाली हूँ. ये तुम सारे के सारे प्रॉब्लम करते हो ना. Let me find somebody else. Yeah, Raghav Sharma. Raghav Sharma. Riya Bajaj.
Yes, ma'am.
Good. I at least appreciate to you responded. Yeah. Could you
Ma'am,
think of
four states.
4 states? Very good. So this will have 4 states. Very well done. Now, anybody else who can tell the states and draw the machine? It's very simple now. Half of the task is done. It's very simple because it's a serial adder. Adder has 4 options with your carry in or the partial carry 0. Your sum can be 0, sum can be 1. Similarly, with your partial carry as 1, your sum can be 0 or your sum can be 1. So you can easily write all the transitions corresponding to the 4 states. So you will have 4 states for sure. You only need to draw their transitions. If I call this as a state A, maybe I'll call it A0 with carry 0, output 0. I'll call it state A1 and maybe output as 0, B0 with output 1, B1 with output 1. So I have my nomenclature which I have done. You can think of your own and devise. In 2, your output should be 0. In 2, your output should be 1. Okay. And in these 2, one of them will have a partial carry 0. Another one will have a partial carry 1. This is what I have indicated by writing 0 and 1. Here again, 0 and 1 to me indicate my partial carry 0 and 1. You can do either way you want. Even if you don't want to use these kind of nomenclature, use A, B, C, D, no problem, but then draw. So now draw the transitions. Now this is when your partial carry is 0. That means you are starting off, your input is 0. And if you get 0, 0 as 2 inputs, your sum will be 0, your partial carry will be 0. So you remain in the same state for 0, 0. If you get a 0, 1 or 1, 0, your sum will be 1, but your carry, partial carry will be 0. So this is the state for 0. Sorry. Where is that? For 0, 1 and 1, 0. Okay. And for 1, 1, you have a different option. You have both your partial carry is 1 and your sum is also, no, sorry. Your sum is 1 for 1, 1, sum is 0, partial carry is 1. So it will be this. Okay. Now from this state, your partial carry is 1, partial carry is 1, again you can get all the 4 combinations of inputs and outputs. Since this is partial carry is 1, I am taking first 0, 1 and 1, 0, where your output will be 0 and you have the partial carry as 1. So you remain in the same state. So this is for 0, 1 and 1, 0. For 0, 0, your sum will become 1, okay, because you have a partial carry, but your partial carry will go off. So it will be this state. For 1, 1, your sum is 1 and your partial carry is also 1. So for 1, 1, you land up over here. Okay, now from here, your partial carry is 0, your sum was 1. Okay, so since partial carry is 0, if you get again 0, 1 or 1, 0, sorry, गलत हो गया. No, perfectly correct. Our partial carry is 0 and output here is indicated as 1. So since partial carry is 0, 0, 0, 1 makes sum as 1. So output is 1, partial carry is 0 in both the cases. If I have 0, 0 and partial carry is also 0, so what I get is sum is 0 and your partial carry is also 0. So you will be here. Okay, the fourth case is left out from here, 1, 1. So if it is 1, 1 and partial carry is 0, so you will get a sum as 0 and partial carry as 1. So you will go over here. Okay, now only this state is left out when your partial carry is 1. Okay, so when your partial carry is 1 and you get a 0, 0. So if you are getting 0, 0, that means there was a 1 added to it, 0, 0. So output should be 1, but carry should not be 1. Okay, output is 1, but carry is not 1. So carry is not 1 means the partial carry out becomes 0. So this is this state or 0, 0. Okay. If you have the other option, which is 1, 0 or 1, 0, 1, 1, 0 or 0, 1, added to partial carry will make sum as 0, but partial carry as 1. So this is the state where partial carry is 1 and your sum is 0. Only one option is left out, 1, 1, added to 1. So it is the same state. So I have drawn the complete state machine using Moore machine. Now it is your task to convert it into a hardware and implement it. Draw the transition table corresponding to it. Choose a flip-flop. Maybe this time you can use any other flip-flop. Use JK flip-flop, okay, and convert it into the hardware, equivalent hardware. So from transition table, write the excitation tables for JK. Now here you have 4 states, so you will need a 2-bit code. So you will need a two flip-flops. Kindly do this process, and if you have done, kindly send me your sheet on email. I repeat my email, and I am recording all those who are sending me the emails. I am recording and I'll consider that is partial internal evaluation. Those who have not sent me even once, you will be in 0. Okay. Subject code will be the subject of the email and send me. And kindly do send me by tomorrow evening. Okay. So that's it. Kindly check the LMS for the next update on quiz. We are planning a sessional quiz on Monday. I believe it is on Monday, 9th. So today is 4th. You have 5 days to prepare. And that we are doing so because we are not allowed to take MST quizzes through Google. So we want to finish off your sessionals. So we already had 2 sessionals. This will be the 3rd sessional. And this 3rd sessional will be from sequential circuits. Okay, it will cover starting from flip-flop latches to the finite state machines, everything. And on Monday 9, you will have the quiz. Okay, so check out the LMS for more details. Any doubt, any question? Okay, if no questions, I will end the meeting over here. Thank you.